So first of all, I'd like to thank the organizers for the invitation, and I would like to thank the audience too for staying until this late afternoon. So today I'd like to talk about the characterization of smooth Schubert variety. So if you see the title, then you cannot imagine how it is related to geometric structures. So I try to explain how we use geometric structures to characterize those kind of Schubert varieties. So let's start with the homogeneous manifolds. So you can think of this as a continuation of the talk by Professor Mo. So he talked about some geometric structures given by the space of lines. So embedded our homogeneous manifold into the projective space in a canonical way, and then we have a notion of lines. And at each point, we can think of the space of lines passing through that point. Then this space of lines can be identified as a subvariety with a subvariety of the projective space by thinking of its tangent directions to those lines. So lines can be determined by its tangent directions. So this can be identified as with a subvariety of this projective space. So the union of all of those things defines the geometric structures on this homogeneous manifold. And actually, so Professor Hwang and Mo showed gave several results on this homogeneous manifold use this kind of geometric structures like global rigidity and some characterizations. So in their theory, what is important is that we can consider those lines in this homogeneous manifold as a geodesics in Riemannian manifolds. So at each point we have a unique line, and at each point we have a unique geodesics. But the difference is that in Riemannian case, we have a geodesics at each directions. But in this case, we have we have special directions where we have lines on which we have lines tangent to it. So that is the only difference. And the basic idea is that the geometry of the space of lines through at one point, so at generic point, determines the geometry of this homogeneous manifold. So today I will use this kind of method to prove our theorem, and this is most of the result is the result is the work with Professor Mo. So this is a joint work with Professor Mo. So let me first explain what kind of problem we are thinking of. So let's start with until the end of this talk, we have everything is happened in this fixed homogeneous manifold. So the problem is rather simpler. So we have a base homogeneous manifold, and take one connected submanifold. Actually, we want to think of irreducible subvariety, but if you don't like irreducible or subvariety, then you can think of a connected subprojective manifold. And think of all its G translates. The group acts on this manifold, and we can think of this family. So this is one orbit. And think of those kind of geometric problems. So the first problem is that find subvarieties of this homogeneous manifold such that at each point we have some G translates which is tangent to this point. So the situation we can write in this way. So S is the whole manifold, and we have a submanifold. So we have fixed submanifold, and we have a transitive action of simply group. So we can translate this to cover the whole manifold. So this is GS0, So this is G prime S0. But the thing is that if we fix one point, then usually we have a positive dimensional family passing through that point. So we have some family passing through this point. So the first question is that whether there is any other way to integrate this one. So our G is tangent to its tangent space, but at each point we have several candidates for the tangent space. And the first question asks whether we can have an integral variety for this kind of system. So I will explain this more later. And the second problem is that, so S0 is fixed, and we can think of its homology class. And so this is a topological question. So fix a homology class and ask whether there is any other subvariety having the same homology class with this fixed one. And the third problem is that we know that we can embed this into a projective space. And let's say that our S0 is also a linear section. Then ask whether if any other linear section is projectively equivalent to S0, then what is those kind of subvariety? So we think of those kind of problems, and in common, there is a G action on those families. So if a subvariety satisfies one of those properties, then the G translate of those subvarieties also satisfies those kind of properties. So this family contains automatically the G orbits of the fixed this manifold. And the question is whether this is the only subvarieties. So for example, if we fix a subvariety and think of its homology class, and taking any other subvariety having the same homology class, then whether they are just the G translates of those ones. So this kind of problems, when you think of this kind of problem, we first assume that this orbit should be closed. Otherwise, then there should be a closure orbit in the closure of this orbit, so that the answer is no. So first we have to assume that this orbit is closed. And the second thing is that we have to assume that the automorphism group is the G itself. Otherwise, usually there is 3 exceptional cases, and in those cases, even though we start with a group, there is a proper subgroup which acts on here. So we can think of it as a homogeneous manifold with respect to a bigger group. So in this case, also the answer is automatically no. So we have to exclude those cases. So for those cases, I will explain later again. And in early 2000, Grimes studied this kind of problems when S is for Hermitian symmetric space of compact type. Irreducible Hermitian symmetric space is a kind of rational homogeneous manifold to be considered here. So what we consider is a problem to characterize a subvariety up to the action of G when S satisfies those kind of proof condition and G satisfies this condition. So the first condition, G S0 is closed, gives the reason why we consider Schubert varieties. So the orbit is closed, then this means that the isotropic group contains a Borel subgroup. So if we started with the irreducible subvariety, then we can say that this is just a closure of a Borel subgroup. So the Schubert variety is nothing. This is the definition of a Schubert variety. Schubert variety is on the closure of an orbit of a Borel subgroup of G. So if we take different Borel subgroup, then they are just conjugated by G, so they are just G translates. So we have to assume that this is closed, so it's natural to consider Schubert varieties. So it is known that when you started with a homogeneous manifold and think of its B Borel group action on this homogeneous manifold, then we have a cell decomposition by, so there are only finitely many B orbits, and each closure defines Schubert varieties of different type, and homology space is freely generated by those homology classes. So this is generally known fact. So let's start with the first question. The first question is that let's fix so now we fix a homogeneous manifold and fix a smooth Schubert variety, and think of the question whether there is another subvariety which is tangent to, this is GS0. This is GS0. So we can think of this problem in this way. So at each point we have a family of subvarieties, family of G translates. And think of all its tangent space. Then this form a subvariety of Grassmannian of the tangent spaces. So this gives rise to a differential system on our homogeneous manifold. So maybe this is a homogeneous linear equation, something like that, I think. So the question is whether there is any other integral variety of this differential system other than the G translates of the Schubert variety we're starting with. So if Z is the integral variety of this differential system, then Z satisfies this condition. So this is GS0. So the question is that the condition that Z has is at each point we have some G which is tangent on Z. But what we are asking is whether we can take this G constantly. Then that means we have just G translates. So this is a rather common thing when we deal with the differential system. So if the dimension of this fiber at each point is 0, then this is just a distribution. Then you know by Frobenius theorem, then there is a unique integral variety if it exists. So there is no other way to integrate this differential system. But if the dimension is bigger than 0, then there may exist a positive dimension of integral variety, even though we fix the tangent spaces. So for example, if we consider this problem in the Grassmannian, then let's fix a flag. Flag means there is a sequence of filtered vector space of dimension 0, 1, and etc. n. In the Grassmannian, if we think of all k-dimensional subspace which contains a fixed k-1 dimensional space but contained in k-1 space, then this is a line in this Grassmannian. And you immediately see that if we think of maximal linear space, then any curves in this maximal linear space is an integral curve of this differential system. But if we think of Grassmannian, sub-Grassmannian, so AB is greater than 1, then they are not linear space and they are sub-Grassmannians. In this case, then the answer is yes. So the integral varieties are just G translates. Furthermore, in this case, if two translates are tangent to each other at one point, then they are equal. So we can say that the family, the G translate of this S0 depends on only one Z. It is determined by the tangent space at one point, so it depends on only one Z. But if we think of this kind of singular variety, then still we get and we get that this is equal to, so this is the integral variety is just the G translates. But in this case, the family itself depends not just one jet, but two jet. So even though the answer is yes, it may be that it depends on more than higher jets. So I give this example to give an idea what kind of the problem is. So let's think about the second problem. So this is characterization by homology class. And so the problem is that if, so we still fix a Schubert variety inside the homogeneous manifold and think of any subvariety having the same homology class as with this one. But in this case, there is only a unique closed G orbit in N2 in this family, the G orbit of S0 itself. There is no other closed orbits. So the problem reduced to prove that we just have to check the family of local deformations. If we can show that any local deformation of this S0 inside S can be obtained by the action of G, then that means this space is equal to. So this is a connected component of this one. But because there is only one closed orbit, so there is no way for this to deform. So the problem can be reduced to show that there is no local deformations in this case. So you can think of a similar problem if by raising this R. So you can think of a similar problem by considering the homology class, which is equal to the R times of the homology class of S0. At the beginning, I remarked that the homology class is determined by those Schubert varieties. So this is a kind of extreme array of those Hon, and Bryant also studied that kind of problem when S is Hermitian symmetric space. But we are thinking of what you are thinking of is general rational homogeneous manifold. So let me say more about some local deformation problems. So today I will restrict to this problem. So whether there is any local deformation which cannot be so whether any local deformation can be obtained by the action of G. If we prove that this is just a G orbit, then that means any subvariety having the same homology class is equal to this closed orbit. So the first method is that it is known that this space, this local deformation, the connected component of this has this dimension. It's the same dimension as the normal bundle of this our subvariety inside S. So if we take H0, then it is known that this space has this dimension. So the question is whether this dimension is equal to the dimension of this family. So if they have the same family and same dimension, then they are equal to each other. So this we can call homological method. But another method is that, and this is the method we are talking about more afterwards. So we are going to take this way. So the problem is that if we have a local deformation inside S, then if G, then because this is homogeneous, then we may assume that it contains one fixed point. Then this proposition says that if we started with the local deformation, then we can think of the space of lines also as a local deformation of the space of lines through E in the space of lines. So we can reduce the problem to the problem on the space of lines. But usually if we think of projective manifold and think of its lines, then it becomes a simpler variety. So, or it becomes variety of smaller dimensions. So we can use induction, or we can prove more easily this fact. So this is the way we are taking in this lecture. So this is another problem. So let me first state the theorems we are talking about this in this lecture. So this is joint work with Bob, and we think of a rational homogeneous manifold of Picard number 1. So this case corresponds to the case where P is maximal, or we can think of the case where the parabolic subgroup associated to a simple root. And think of first homogeneous ones, homogeneous submanifold associated to a subdiagram. So there are several examples of subdiagrams. If we started with the Grassmannian, then for the Grassmannian, the marked Dynkin diagram for this is the Dynkin diagram corresponding to this is AN type. So AN type is the group SLV. So SLV acts on here transitively. So Dynkin diagram is AL type. And this K means we have to choose a parabolic subgroup associated to this simple root. So this is case simple root. So the whole diagram represents this homogeneous manifold, and this is the marked Dynkin diagram of this homogeneous manifold. But the subdiagram means that we just took a connected part of this diagram which contains this marking. Then this represents a sub-Grassmannian that we have seen before. So the subspaces of k-dimensional subspaces which contains this smaller one, but is contained this bigger one. So FA is this place, and FB is this dimension. So B is here, A is here, K is here. So this is an example of a homogeneous manifold associated to a subdiagram. And the theorem says that if we think of those kind of homogeneous manifolds, then any subvariety having the same homology class as this one is obtained by the action of G. But there are some exceptions, and this is the only exceptions. So the first exception is that when S is associated to short root, then it is already known by the work of Professor Hang that there are more lines than can be obtained by the action of G. So in this case, we have counterexamples. And furthermore, there are this kind of homogeneous manifold. So if we see this homogeneous manifold, then this corresponds to the case when we think of the symplectic Grassmannian. So in this case, the Dynkin diagram is a CL type, CN type, and the vector space is complex vector space of dimension 2n with a symplectic form. This omega is symplectic form. So now we think of all k subspaces, but which is isotropic with respect to this symplectic form. So this S is represented by this marking. So this place also case simple root. So this is the whole diagram is the marked diagram of this homogeneous manifold. And think of the same thing. So think of the k isotropic subspaces which is squeezed by two isotropic subspaces. So k minus 1 is here, and B is somewhere here. It does not have to be this one, but anyway somewhere before here. So this subdiagram represents this homogeneous manifold. And this is 2, and this is 2. And the reason why we have a counterexample in this case is that we can think of a little bit bigger diagram, and this diagram represents the exceptional cases the cases of this one. So in these cases, this is just the isotropic subspaces of complex vector space with a skew symmetric, with a symplectic form. But symplectic form is skew symmetric, so every one-dimensional subspace is isotropic. So in this case, this is just projective linear space, and this is exactly the case. So in this case, the Dynkin diagram is just a CL type, but we have a bigger group, SL, which is shown here. So in this case, every subdiagram has some counterexamples, if we think of it in this way. So everything the others are same. And let's think about the symplectic Grassmannian case more. So if you symplectic Grassmannian is defined by taking all isotropic subspaces of the same dimension of this vector space with the symplectic form. And the way to get Schubert variety is to fix an isotropic flag. So isotropic flag means this is a usual flag, but it has this kind of condition. Its orthogonal part is, orthogonal complement is this one. And think of the space or isotropic K subspaces such that which contains this small subspace, but which is contained the bigger one. Then we got a smooth Schubert variety. Sometimes it is called odd symplectic Grassmannian when it has this dimension. So we can prove that in this case, for this particular Schubert varieties, we can show that any subvariety having the same homology class can be obtained by the action of G. And actually, we expect that. I mean, in other cases, like when A is K-1, then we have counterexamples. So this is the same as well. So this is two theorems that we are talking about. So we are thinking about a pair of homogeneous manifold, and one is a homogeneous manifold of Picard number 1, so associated to a sync root, and the other one is homogeneous manifold obtained by taking a subdiagram, and the other one is symplectic Grassmannian. So this is the case where S is associated to a short root. So in some sense, this is some should be treated in a different way, and this is a smooth Schubert variety. So actually, this is we expect that this is the only non-trivial smooth Schubert variety. That means when S is associated to a long root, then any smooth Schubert variety should be homogeneous. So there is no other non-trivial example of a smooth Schubert variety when S is associated to a long root. So for example, when you think of Grassmannian, then any smooth Schubert variety is obtained by taking two flags. Maybe one may be trivial, the other may be trivial, but anyway, it can be obtained by taking two flags. This partial flag, and think of all subspaces which contains the smaller one and which is contained in the bigger one. So the method is to use the variety of minimal rational tangent, but in our case, our manifold is just a projective manifold and which is homogeneous. And in this case, our manifold is covered by lines. So we don't have to go to this far, but we just think about the space of lines which are contained in this homogeneous manifold. So in this case, if we take a smooth Schubert variety, and if we take its local deformation, then we can show that this is still uniruled by lines, and because this has Picard number 1, so this has also Picard number 1. So until up to now, the most of theory about variety of minimal rational tangent is for the uniruled manifold of Picard number 1. So this is the reason why we check this condition. And if G is uniruled by lines, then we can think of the space of lines, and also we can think of the space of tangent directions to these lines. So we also have some geometric structures in the projective bundle. So what we are going to do is that if we first started with the S0. So S0 is, you can think S0 as a model geometric structure, and Z is some curved version of this model structure, and ask whether this covered geometric structure should be the model structure. So this is the kind of problem. So we continuously fix this homogeneous manifold and take a smooth Schubert variety, and at each point we have a family of submanifold passing through this manifold. So family of submanifold obtained by translate our fixed manifold by the group action G. But think of the subfamily which pass through this fixed point. Then the lines through this point is again a family of submanifold inside here. So if we draw a picture here, then in the ambient manifold we have a space of lines. But some lines, not all line is contained in this subvariety. So some lines contained in this subvariety. So this is lines passing through this point, which are contained in this fixed one. But through this point there is another one which can be obtained by the action of G. So here we have another family. But still, these lines should be contained in this S. So once we deform this S0 by the action of G, then we again have a family of the family of submanifolds consists of lines. So this notation this represents the space of all lines passing through this point. So this is ambient manifold. So think of all space of lines passing through this point, but contained in this smaller subvariety. And if we move our G, then we have a family of submanifolds inside here. So the first assumption is that this is again a family of submanifolds, and if they are tangent to each other, then they are equal. So the first assumption is that this family obtained by taking the space of lines depends only on one Z. So first assume this one, then we can say that any subvariety uniruled by lines and Picard number 1, and if this is a kind of curved version of this family. So at each point we have a G translates having the same space of lines. So this is a little variation of the problem, but this problem can be solved by using the deformation theory of lines. So the first proposition is that if we assume that our model space depends only on one Z, I mean our model family has this kind of property, the space of lines depends only on one Z, then we can say that any curved version of this submanifold any submanifold having the curved version of this geometric structure is just a G-translate of this model space. So this is the standard embedding of the S0 up to the action of group. And here we use the deformation theory, but just let me explain by picture. So the theory we are going to use is that at the beginning I remarked that the lines in the projective space or the lines in the uniruled manifold, the uniruled variety can be considered as geodesics in the Riemannian manifold. So what we are going to do is to transport the informations of the geometry of at one point to the other point. So let's fix one point Z and think of the space of all lines through this point. Then it can be think of as a variety contained in the projective space, just taking the tangent directions to these lines, then we have a variety and we denote it by CZ. So CZ is the space of all tangent directions to the lines passing through this point. So because this is line, we can identify the space of lines with the space of these tangent directions. So let's take another point along this line and think of the space of all lines. So then we can think of this as a projective variety by taking its tangent directions. But the deformation theory of minimal rational curve says that the geometry of this space gives some information on the geometry of this space, but not the whole information, but the information on the tangent space at this point. This alpha is the point corresponding to this direction. So along this line, we have some particular direction which corresponds to the tangent directions of this line. So at x we have the direction to this line, and the deformation theory says that if we have 2 points and think of the space of lines passing through this point, then the geometry of this gives some information on the geometry of here. So the geometry can be transported through this line, but not the whole information we cannot get the whole information, but we can get the information on the tangent space. This is a place where our assumptions on the tangency works. This is the reason why we put this condition. Because let's think of the case now, let's think of our proposition. The proposition says that if we start to, let's say it's a smooth Schubert variety and this is the model case, and we have a curved version. And what they have is that at each point the space of lines looks like this one. But we are asking whether we can take the constant G for the whole our manifold. So let's assume that there are two manifolds, so Z and our homogeneous manifold having the same space of lines at this point. That means they share the same lines through this point, so they share the locus of those lines. But this does not mean that they have the same space of lines at another point. But our assumption says that, but the deformation of theory says that we cannot say that they have the same space of lines at this point, but we can say that at least they are tangent to each other. So if we started with subvariety with having this kind of property, then by this assumption we can say that they are the same at this point too. Because they are tangent to each other by this deformation theory, but by our assumption, they are the same. So they share the same lines at this point too. So we can continue this process until we cover the whole variety. So they share the same open subset, so they are equal to each other. So this is the proof for the proposition 1. So this is the main idea, how to prove this kind of things. So when we have this kind of curved geometric structure, then we can uniformize this G by 1G. So we can say that Z is just G translates of our model space. So in the second, to prove our theorem, the second assumption is that X is the space of lines passing through this point, and X0 is the space of lines passing through this model space. And the second assumption is that any local deformation of this can be obtained by the action of the isotropy. Then we can say that, so we can say that any local deformation of S0 is just G translates of our model space. So by the proposition at the beginning, for our problem, we just consider any local deformations of this model space. And because G acts on S transitively, we can assume that they share the same point. So that we can think of the space of all lines passing through this point. And as I said before, the space of all lines passing through E contained in this ST is a local deformation of the model space. And by the assumption, because we can think of this as a local deformation, so we may assume that they are equal to the action of G, action of the isotrope, the action of G, because the isotropy acts on G, E. And yeah. So if we fix T, then, so if we fix T, after fixing T, we can think of this as a deformation of this space again. So by this assumption again, then we can say that this is locally, we have this kind of G translates. Then by the proposition 1, we have a local open set which having this kind of property, so that we can say that this is just standard embedding. So we can obtain this by the action of our G. This is because of the proposition just we proved. So this is how it worked. So it just have to show that we assumed two things. This is the second assumption, and we have one more assumption. So it remains to show that we have those kind of properties. So this is the first assumption, and this is the second assumption. So for the pairs of the manifolds, Schubert varieties and homogeneous manifolds, we have to check this kind of properties. But usually this is much easier than the second one. And for example, in the Grassmannian case, the homogeneous variety associated to a subdiagram is just sub-Grassmannians. Near sub-Grassmannians. In this case, the space of all lines passing through one point is the product, just the decomposable vectors in these tangent spaces. So they are just product of two linear spaces, and the space of all lines passing through this sub-Grassmannian is the product of two linear subspaces. This is a linear subspace of this one, and this is a linear subspace of this one. So any local deformation of these two products inside this bigger product is just the L translate of this group. So we can, this is just the product of two linear spaces. So we can obtain this by acting this product group. So this is the reductive part of the isotropy. So this is the Grassmannian case. And there is another interesting class of homogeneous manifold which one may call orthogonal Grassmannian. In this case, we fix a non-degenerate symmetric bilinear form. And if we take isotropic flag again, then the space of all isotropic K-subspace is a homogeneous manifold, and on which we act SO, we act on here transitively. So in this case, we can think of also the sub-Grassmannians again. So think of the isotropic K-subspaces which contains this smaller one, but contains in the bigger one. In this case, the space of lines passing through one point, so passing through one fixed K-subspace, isotropic subspace is just a product again. But in this case, we have a symmetric bilinear form, so the second one should be isotropy with respect to this bilinear form. So we get a product of projective space and a smooth quadric inside here. So this is a Segre embedding. And for the smaller ones, for the sub-Grassmannians, this is similar to this one, but this is a smaller quadric and smaller projective space. So in this again, any local deformation of those two products is again a product, and any local deformation of smooth quadric is again obtained by the action of S orthogonal group. So in this case, we can also get this kind of result. And the proof is similar when S is associated to long root. But when S is associated to short root, so the case where S is symplectic Grassmannian, then the variety of minimal rational time, the space of lines is more complicated. But what is important is that, let's say that the smaller one is just dimension 0. So this is the space of all isotropic K-subspaces, which is contained in the hyperplane. So in this case, the bigger one, the whole space of lines can be have this kind of description. So epsilon is this is the space of lines is just the projectivization of the vector bundle on this projective linear space. So if we compare this with this, in this case, let's see this. So this case, this can be think of a trivial vector bundle over this projective linear space. This is trivial vector bundle, but in the symplectic Grassmannian case, this is not a trivial vector bundle, but this is a product of trivial vector bundle with non-trivial line bundle. So it is complicated that this much, but because this is hyperplane, the basic reason, the reason is that the reason why we have this kind of result is that because in the symplectic Grassmannian case, so when you have even dimensional complex vector space with the symplectic form, if we take hyperplane and if we restrict this omega to this hyperplane, then still we may get a skew symmetric form which has a maximal length. So this is generic in the sense that there is no any local deformation of this space is again have this kind of rank. So even though this is a little bit, so we need some more works to do, but in this case, so we can show that this local deformation is again, so this is the model case. And if we deform this subspace and deform this space of lines, we still get a hyperplane such that having the property this kind of things, so that we can think of any local deformation as a translator of isotropy. So in this case, we need the full isotropy. In the former cases, like the long root case, we don't need the whole isotropy. We need just the reductive part of isotropy. We don't need the full isotropy. But in the symplectic Grassmannian case, actually we need the full isotropy to get this kind of conjugacy. So any local deformation of the space of lines of this model space can be obtained by acting the isotropy of this one. So this is this argument proves that any local deformations can be obtained by acting the isotropy. And the first is, for example, in the first case, if we translate by this action, then we have another spaces. But if they are tangent to each other, then this tangent space uniquely determines this FA and FB. So this is unique. So by this property and by the proof, we can show that in the families as in our theorem, we can get any subvariety having this homology class can be obtained by the action of our group, the full group. So the theorem is like this. So this is the homogeneous case, and this is some typical, some special case of short root case. But for the short root case, this is the we could compute the things only for this case. But the difficulty is that in general the singularity of Schubert variety itself is a difficult problem, so that we couldn't. It's not easy to find to determine which one is smooth or singular. So in this case, this is known to be smooth. So we just take this one and check whether this has this kind of property. So this is true, and I expect that in other cases they are just homogeneous ones in this case too. So. But that is just expectation, and this is the end of my talk. Thank you.
Are there any questions?